Hi, Sherry, how are you?
I'm good.
We'll get started, okay?
Okay.
And then because Sarah is out of town, and also Helen is in competition, so we can get started. We are not waiting for them. Okay, so today we are continuing for the adjacent list last time. And then last time we actually is focused on building the graph. So today we will be focused on doing the depth first searching. So visiting each node, okay, that's actually our main purpose. So what happened to the graph is it is different from the tree. So when we do tree don't have the cycle, okay, tree don't have a cycle. So you actually go down each node. And each node has a child or grandchild. Okay, so you go down each node. So when you go down for the depth first searching, you just keep going, keep going, keep going, return, and then next one, and return, next one, return. Okay, something like that. So there's no need that you keep track of which node you already visit or not, because usually go depth first, you visit certain node and certain node you won't visit. So just left child first, and then middle, and then right child. That's actually called in order traversal. And depth first in order traversal. That actually is okay. But right now we are talking about graph. Graph is different. So graph is different because graph you go into the graph, then you do visit, you visit this node, then you go depth first, and then you return. So next time you may visit the same node. When you go depth first, okay, you may visit a different node. So you have to keep track of whether a node that you already visited or not. Okay, so to do that, we need to keep track of whether a node has been visited or not. So I directly copy last week's graph class to a new directory called map list. Okay, I copy it to here. So we are going to modify from here. So first thing that we will need to do is we do type define. Okay, vector Boolean type. Okay, and then we could keep this one as this one is called deleted. Okay, so deleted, and then let's call it. We have V. We have use P. Let's call it. We have vertex. We have H. Okay, and we call this one as VT. Okay, let's call it deleted. Okay. So it's actually a vector or Boolean, we call it that. So when we add a node, we push back the node there, and then we create H to there. So we actually should do this. We should do bt dot pushback. Force. We put a force into the vector of Boolean data type. Okay. Now we would actually need to have a function. Let's call it void. And then let's do reset. So need to reset, we will actually make sure every node in the visited are we actually set to the unvisited status. So for okay, every Boolean b from vt, okay. Let's see that actually do this. No, this one is not good. Let's do for integer I equal 0, I less than VT the size. Okay, I increase. And let's say VT's I's value equals false. So this one will reset the VT. Okay. So let's assume that we have 4 nodes, right? So and then use these are called A node, B node, C node, D node. And then each one of them actually has a node, it have a vertex for each node. Okay. And then there is a related array to be false, 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 and you can reset it to be false. In the graph, okay, you reset it, then we know that they are all unrelated. And then we actually would go for the depth first searching. Okay, we will actually go for the depth first searching. Okay, let's do this one called okay, so we actually do depth first search on the graph. Okay, so we will get started from the first vertex. Okay, we'll get started from the first vertex. So let's call it depth first searching helper function. Okay, we'll get started from the vertex node 0. Okay, so right here, if v the size equal 0, we directly do return. We don't visit anything because we don't have the node. And if not, we are going to visit the first node. First node is actually, let's see. Let's actually get started with 0. Okay, just do 0. Let's actually do V0. Okay. So you actually pass the, let's see, if you have A, B, C, D, you get started from the first node. Okay, you get started from the first node. If you don't have any node, then you return, you don't do any searching. Okay, so here that's actually, well, we may use 0, may use V node 0, then let's do it later. Okay, so here let's do, so this one actually is, when you do depth first searching, you go started from one node. Okay, but you do need to have a helper that will do recursive searching on all the node. Okay, you need to do recursive searching on every node. So this one, let's call it void. Okay, depth first searching helper function. Okay, and then you actually do on the node n. Okay. So on the node n, you have a node n, you do relative on them. Okay, let's actually try this. Let's don't try mode n. Let's try integer n. Okay, integer. I mean, no, don't call it integer. Let's call integer t. Okay. So here let's use a 0 instead of this. So this one is a number. Okay, this one is a number. So this one is number t. So number t means that you actually get this one. Let's actually call it A, B, C, D. So you get started from node 0. Then when you go there, you will actually visit all of the edges, okay, for the neighbor nodes for it, okay? So one thing is that you want to do this, first thing is that you want to do C out, okay? Then you, let's see, you have the V's, E, okay. So each node you would like to print out the data. So this node, when you print out the data, you do toString for it, okay? So right here, you do that toString. Okay, you print this node first. Okay, so you read this node and you print it first. Okay, let's see. toString, something wrong. Let me look at it. Graph. So graph, you actually a node don't have the node don't have a toString. Oh, node don't have a toString. Okay, I'm sorry. Node don't have a toString. So right here, it's actually you directly, but you do have the converter, so we do directly print it out. Okay. And then you know the T, so you want to do here you do have the H is E, okay. So that each edge is actually a vector of the node pointers. Okay, so you would do you actually is vector actually is a vector of the you will have edges. So here let's do edges. Okay, and then do neighbors. Okay. And this neighbor will be equal to actually ET. Okay, this one getting all the neighboring edges. Okay, so right here you would to set your VT's T to be true. Okay, mark the node already visited. Okay, so you mark every node that already been visited. The current node already been visited, and then you actually go to each edge, okay? And then you would visit every edge, okay? So you do for integer I equals 0, I less than, let's see, I less than, okay, right here, actually, you need to do one thing. If VT of the T, okay, equal true, then you will return. Okay. So you've already been visited, you will return right away, and you don't go visit it. Okay. Otherwise, you go for every actually. Okay, you go for every neighbors. You go for the every neighbors. Okay. So you do know the pointer P. Okay. Be equal to neighbors I is a pointer, okay? So you go for the neighbor pointer P, okay? And then you will say the integer K, that's index K, okay, that's equal to the index of the body of the P, where the body pointing to. Okay, it's a pointer, P is a pointer, so the body of P is getting an index K. So that K actually is your number. Okay, I'm sorry, that's the key. Okay, that's key. So let's see. Actually, this one we need to be careful. So the key actually get key is getting the key value. That's not the index. Okay, so we don't do that. That's different things. Let's see. This one actually we would need to know about the ages index. Actually, you go down to the graph. And then you want to get key. Okay, you want to get key. So this one, you actually is not getting key. You should do differences. Okay. So you do for integer j equal 0, j less than the vertex the size. Okay. So you would do this, and then if okay, let's actually try different. Okay, let's actually delete this one. Now actually let's use a different function. Okay, so right here let's have a function. So it's an integer, okay, and then index of. Okay, let's use the index of function. So right here we are going to look at the node alias n. Okay. Okay, so integer p equals this one. We are going to use n bucket key. Okay, it's k. Okay, and then okay, and then for integer I equal 0, I less than that size, I increase. Okay, and then if is I vector T equals K. Okay, that means that you know between the T. So this one will return I. Okay, and otherwise we will return -1, means that we don't find the key. Okay, so right here we actually we say integer K equals index of body of P. Okay, we actually use the body of P to find a key. Okay, so if okay, K less than 0, we would do continue. We won't search. Continue to search. Okay, if we cannot find the index of a certain node, we don't do it. Okay, otherwise we'll do that first. Actually helper on the k value. So actually recurse the traverse. Okay, so this one is our depth first searching helper function. Okay, so let's actually review this one more time. So we want to do a depth first searching. So let's see, these two functions will need to be, let's cut it. Need to be on top of the depth first function. Okay, it should, because they need to be called by that. So now let's actually review it a little bit. Okay. So this one, index of function is to search a node's index. Okay. So you actually get its key and then make sure there's one node of the key is the same with this node key, and we'll return the I. Okay, so this one is trying to find the index, so there's no problem. Next one, we will do depth first searching on a graph. So we will go to the node 0 first. Okay, if the size equals 0, we do nothing. Otherwise, we're starting from the first node. Okay, node 0. So this one can be node 1, node 2, whatever node you have, but let's use the 0 as our initial node. And then you go into the recursive searching. So if a node you already visited, then you would just return. Okay. Otherwise, you would actually do visited that node. Okay. You print that, and then you will actually you will set that node to be true. Okay. And then you will go to the edges, and then you go to every neighbor, and then you actually get the neighbors, and then you get the neighbor's index. And if that neighbor's index you cannot find it, then you return. Otherwise, recursive to visit any neighbors. So this one is depth first searching. Okay. So this is a depth first right here. We would also do return if the size 0 return. Otherwise, we will also do the function reset. Okay, when you start in the EFS, we also reset. Reset means that we make sure every graph node actually there's no every node is reset to unvisited status. So now this test graph.cpp, let's actually copy this file and then paste. And then let's change the name to test graph number 2. Okay, so we build a 3 node. Okay, we just started with 3 node, and then we build a graph. And we add a 3 node and edges. So right here, let's don't do this one. Okay, let's comment it down. And then what we will do is that the graph, okay, when we will run DFS, and that's actually after we finish, let's do cout endo, okay? So that will call that function, and then call that depth first searching function, and then start to do visiting, and then print out every node. Okay, print out every node. So that's actually save it, and then let's run this test graph 2. Okay, this one we do not put any input, so this one we can use a run code directly. Okay, so we actually visit 1, 2, this. Okay, this different node. So then that's actually print for 2 line. Let's do visiting one more time. Okay, so we visited twice, so it's okay. Now let's copy this test graph number 2 to another one. Okay, this one is actually called it test graph number 3. Okay, this is test graph number 3. We are going to build a different graph. Okay, so let's assume that we do have, let's do A, B, C, D, E, F. Okay, that's assume that we actually do this different A, B, C, D, E, F. And then the node number, let's use 1, 2, 3, 4, 5, 6. Okay, that's actually build this graph. So we have the A and then set 1A, B, 2B, okay, C, 2C, okay, 3C. Okay, let's copy this different node. And then put it right here. Okay, and then this one is set it to be E, 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 and then F, and then F. And this to be 4, 5, 6. And then this two given node, we set it to B, E, and F. Okay, so this one we actually have this. And then we are going to add another 3 node. So let's put it over here. This one would be D, E, and F. Okay, these are different D, E, F. And then after that, we would add age. So originally we had A, B, okay, covered, B, C covered. And then now we would add AD node. Okay, AD, okay. So AD. And then let's copy it, okay? So next one we will have the CDH, and then we have CEH, and then we have CFH. Okay, so this one totally 6 edges, 1, 2, 3, 4, 5, 6. It's AB, BC, AD, and then CD, and then CE, and then CF. Okay, CF, this one should become. Okay, done. And then we will print out the graph once using the depth first searching, and then we actually print out twice. Okay, so that's done. Let's actually clean it. Okay, so let's see how you read it. Okay, so the graph is, I'm sorry, let's actually redo it. The graph is A, B, C, D, E, F. Okay, so you will go A first, then B, then C, then D, coming back, and then you go E, okay, coming back, and then you go F. Okay, so these 3 are the actually the children of the C. So you actually do A, then B, then C, then D, then E, then F. Okay, so that's the depth first searching orders. Okay, any question? Any questions so far?
No.
So this is depth first searching, okay, and I visited it twice to make sure that the graph would be resetted properly. When we do reset means that you are going to clean the record for visited. Okay, for visited. So this one is a graph. So as you can see, this graph operation, first you need to set up the graph. It's very complicated. And then you actually, this one is traversal. You need to set up how to do traversal, okay? Okay, so this one actually is called map list. It is directly in our today's program. Okay, so now I'm going to do this. Okay, we're going to go for one example by the textbook. So right here, I already created this depth first searching chapter. Okay, I'm going to create a new folder. This one called. Wait, I'm sorry. Let me actually check the name. So now we are going to go for the next one. It's called word later problem. Okay, let's look at this word later problem. So let's call it word later. Okay. So now let's actually create a new directory called word later. So inside this word later problem, we are going to go back to our textbook. So let's look at what is word later problem. Okay. So to begin our study of graph algorithm, so the previous one we used the so-called adjacent list to build a graph, and we do depth first searching. Okay, so that's done. Next one, we are going to do this one, 9.7 word later problem. So this is one example of using the graph to solve problems. So later we do have a lot of problems. Okay, that's actually what we want to do for a graph. But at this moment, let's focus on the first problem. So this problem is called word later problem. So begin our graph algorithm, we consider a puzzle called word later. Transform the word fool to the word sage. Okay, that's the purpose. So fool to sage. In the word later puzzle, you must make a change occur gradually by changing a letter at a time. And each step, you must transform one word to the other. You are not allowed to transform the word from a word to a non-word. Okay, the word later puzzle is invented in 1878 by this one. Okay, so whatever. So we have fool, pale, sail, sage. Okay, whatever. So you are going to change from fool to sage. And there are many variation of the word later puzzle. For example, I'm sorry. You might be given a particular number of steps in which to accomplish transformation, or you need to use a particular word. Okay. In this section, we are interested in figuring out smallest number of transformation needed to turn the starting word into the entire words. Okay. Not surprisingly, since this chapter is on graph, we can solve this problem by using a graph algorithm. Here's the outline of what we are going. Okay, first you need to build a graph for sure. Okay, next you are going to use the graph. Okay, known as breadth first searching to find efficient paths from the starting word to the ending word. So I think that you get started from fool, and every time you change it a letter. Okay, so you came from fool, then pool, then Paul. So you change a letter at a time. And then you change it for Paul. Okay. And then you change it for pale. And then change it for sail. I'm sorry, this. And then you change it for sage. I'm sorry, I used the wrong one. So each step you go through the map and then you actually change for one letter and then you go from your 4 to 6. So this is called word later problem. Is that okay so far? Is that okay so far?
Yeah.
Okay, let's look at the problem more carefully. So this one actually you have a graph. So graph actually you do build up the word later problem. So you have fail and another letter of 4. There's one letter distance from I to L. Then these two words are neighbors. Is that okay? So fail and forward, they are neighbors. So when you have one letter come in, you actually check the letter, who is your neighbor, by checking if the word is one letter distance from your original word. So you may have an array of words starting from the first one, and then you actually, this one's a fail. Then you have 4 coming in, so 4 is one letter away from it. So these two have the age. Is that okay? And then gradually you add more later into there, and then you build a graph like this. Is that okay? Hello, is that okay?
Yeah.
And after this, you actually know that you are getting started from 4. So this one is you are searching from here, and you do that first searching, you go to your search right here. As long as you go to the depth first searching, and then there's a node that you equal to that. And then that's fine. So this one, if there exists a path, say let's do A, B, C, D, E, F. So as long as if you have the A to F and you want to find a path from A to F, the depth first search will definitely reach there. The depth first searching will definitely reach there for the whole path. There should exist a path that you can go there. Okay, so this one is the idea. Okay, so let's actually copy the whole file over. Okay, let's actually copy this one over. Okay, so this one, let's call it word later CVP. Okay. Okay, let's look at this one. Okay, let's look at this one. This one actually, it has a file string, IO string, okay, whatever. So there's a vertex. Each vertex that actually is a node. Okay, so each vertex you have a string ID. So you will say your pale or something. Okay, cool. Okay, that's your string ID, and then there is an edge. So that's when you connect it to. Let's call pole. So there is a pole that's your neighbor, and then there's a weight 3 on your connected. Okay. So that's your vertex. So vertex, you have a key. Okay, key is actually a string you assign to your lighting when you created your vertex. So this one vertex is actually similar to end node. Okay. And then you add your neighbor with a weight. Okay. That's your neighbor. So each vertex has a ID and its neighbor connected to. And then you actually can do get connections. So you actually go through every connector, okay, by pushing back the first to the keys. So keys that you actually go breadth first searching, you go to your every neighbor you have, and then you push them into the keys. So keys keep track of all of the connections that you have, all of your neighbors. So this one returning all of your neighbors. So get ID, you actually get the ID. Get weight, you get a weight, okay? And then you can print out the node, okay? A vertex, you can print out the vertex. Okay, this part, okay. So when you build a graph, you kind of had a vertex list. Okay, so you have the word and the vertex, word and the vertex. Okay. So your word is the keyword, say, pool that you have. And vertex is the representing node that you have. Okay. You keep track of the vertex and direction or whatever. So you set the graph to be directed, okay, whatever. And you add the key, a vertex with the string key. Okay, so when you work at the key, you increase the vertex. And then you create a new vertex, and then you assign to the vertex list. So this one is also an array of the, this one is also an array of vertex. Okay, so your vertex list is array of vertex. And that actually, I'm sorry, it's not an array of vertex, it's a map of vertex. Okay, map of vertex. Okay, this one, okay. And then you can do get vertex. Okay, get vertex, you use a string, you will return you the vectors for you. And then you will check if the graph contain the vertex or not. Okay. And then you will add age, okay. Cost equals 1. Okay, so if both string the graph content is okay, and then you will add the neighbor with the cost. Okay, so this add one age. Okay, and then third vertex, you go through every vertex and then return. Okay, print it. So next one is the printing part. Is okay. So here you have the array of the word, you put them into the graph. Okay. And then you go to every word, okay, and you try to actually make sure that the frame will be pushed into the edges. Okay, frames will be pushed into the edges. Okay, that's it. So here you do enter every word into it. Okay, you have every word into the array. And then you create a vertex, okay, a word list of this much element, and you build a graph upon the words, and then you do converting the graph to graph. Okay, that's actually pretty simple. Okay, so this one just traverse through the graph. Okay, so this one show you each node, full to full. Okay, that's an edge, and then full, and then fail to full. Okay, this one actually show you different vertex and node. Okay, so that will build, this program basically will build such a graph. Okay, and we haven't tried to find a path yet. So this one will build a graph, okay? And it's using the maps to build such a graph. So as you can see, I use the node and string to build it, and use the vector of the node to build it. And this one is an example of using the map to build it. Okay, and using the map to build it is better because you can directly search for a node using the key value that's actually a string. Okay, and mine I have to do index of to find the node. So when in the computation is a little bit harder for my way. Okay. Now this one is actually continue to the next topic. So now you actually implement the breadth first searching. So breadth first searching will be different from depth first searching. So you do have A, B, C, D, E, F. So breadth first searching, you will do A first, and then you do B or D. Okay, and you don't find the answer, you will try C. Okay, B will find C. Okay, B is the only child in this one. And then your D, you also your C already be visited. You will also do C. Okay, if you haven't found the answer. Okay, and then C you do E and F. And then this C you also do E and F. And you may also search for B right here. This one you may search for D right here. Okay. And D go back to A, but A will be deleted. Okay. So anyway, these are the breadth searching. So breadth searching, actually, each time you do searching, you need to push the node that you want to visit to a vector. So you visit A, then you put B and D into the vector. Now you're going to visit these two nodes. Okay, and then you take B, okay, and then B will have C, then you push C into there. So you will go depth first by using a to be visit list. Okay, so there is a to be visit list. Usually that one is the one that you keep track of it breadth first searching. Okay. So this one, let's see. This is Python. Okay, I'm sorry. How comes up we are at Python? This one is Python. Okay, so here we have another one. Here the program actually is right here. Let's actually copy this one. Okay. Okay, up to here. So this one is actually created. Let's call it or later. Web first searching. So this version is the same graph, but with the web first searching. Okay, so this one is better. Let's actually look at it. Okay. I make a wrong name. Let's rename it as CPP. Okay. So this one, there's a queue. Queue is used for the breadth-first searching to buffer the node to be visited. Okay. So you have a connected to, you have the vertex of pointer. Okay. Previous one, something like that. Okay. Okay, your graph, okay, and then this one, I think it's the same. Okay, right here you do have the breadth-first searching. You have a graph coming in. You have case study from your initial node. Okay, And then you start at this, you set to be this, and then you have a queue of a vertex queue. That's the one you want to get started. Okay, so you push your start node to the queue. And then while queue not greater than 0, you actually use the front, you pop out the front, the first element, that's your current vertex. And then you go to its every connection that it has. Okay. And then you actually visited that each one of them if you haven't been visited. Okay. You will go to there and then you will go push every friends, you push every friend into the to be visited nodes. Okay, to be visited node, you go visit every friend that you want to go to the node. Okay, and at the end you return the graph. So you would actually do breadth-first search and you get started from full and you do traversal to pair. Okay. Okay, so you build a graph based on depth searching based on full. Okay. And you traverse to each individual node. Okay. Okay, so it's coming from PALL. Okay, actually, it's actually from full to full to pole to pair. Okay. Okay, to pole. Is that okay? So this one, if we do the same problem that it is shown in the previous one, let's actually get started from full to sage. Okay, let's actually do full to sage. So this one, we put the sage right here. And you do from full to sage using the breadth-first searching. Okay? Is that okay? Hello, is that okay? Okay, so today we actually working on this word data problem. And we also work on our previous one actually that do depth versus searching and breadth versus searching. Okay, so these two searching way are the main searching one when you do traversal for a graph. These are very fundamental ideas. Okay, these are very fundamental ideas. Okay. So here it does has the analysis for the breadth versus searching. Okay, but it's okay. We actually it actually is an order of V plus V plus E. Okay, that's the searching time. Okay, so we finish up to the 9.10. So now I'm going back to the adjacent metric. Okay, I'm going to back to the adjacent metric. So far we have been using the adjacent list. Okay, we have been using the adjacent list. And then we implement the so-called depth first searching and the breadth first searching. So let's go back to look at the adjacent metric. Okay, adjacent metric is that your connection is using the metric. Okay, but right here they don't have example. Let's actually search for an example. Okay, let's look at the adjacent matrix. Okay, so adjacent matrix is different from your adjacent list. Adjacent list, you use a list to provide your ages information. Okay, so here you use a metric to do it. A metric wasting memory, but actually it's array access, so it will be faster. So let's assume that here you have a graph like this. Then you build a vertex with the index, and then build the edges using two-dimensional array. Okay, using the two-dimensional array, build your edges. So basically, let's actually look at this example. Let's copy it. Okay. So I'm going to go back to here. This time I'm going to open a new folder. So I'm not going to put a map list or word later. So right here, I'm going to create another one. Let's call it map matrix. Okay, let's call it map matrix. So this one, let's call it okay, let's use this one. So let's call it graph matrix. Okay, and put it right here. Okay, so this one, you have a IO string, okay, and you define your V as a 6. So that would be 6 node, okay, so that is 6 node. And then you create a matrix of 6 by 6. Okay, that's actually the matrix 6 by 6. So when you add the edge from and to, you actually mark the matrix to be 1, 1. So you have a U to V node. So this one is actually unidirectional map. Okay, so you actually two node would U will go to V and V will go to V. Okay, and then you have the twin matrix. You will go to visit every number. Okay, you will print out the relationship of each one. Okay, so you create an add matrix of this. Okay, and then you add the different edge on it. Okay, and you print the matrix. So let's see. And that's wrong. Okay. So basically, you preview the adjacent matrix. Okay. Any questions so far? Any questions so far? Okay, so this one, okay, this one not too hard. Okay, you build a graph using the adjacent matrix. Okay, and the unidirectional map. So next one, we may want to do traversal on it. Okay, let's see. This is list, adjacent list. So basically, what I want to say right here is that this one actually a graph. And this graph actually just using the two-dimensional array, okay? And then there is no extra node informations. So this one, if you just use the key like this is okay. And you actually can also create an array. And then you put the array to be the key number. Okay, each one you actually put the information of the node in the array. So that still will work. So basically adjacent matrix, if you use a two-dimensional array and they just use the node ID to identify each node, okay, that implementation of graph will be pretty easy. Okay, so adjacent matrix implementation of graph is easy, it's just a two-dimensional array. Okay, the vertex you can use a one-dimensional array for it. It will be easier. Okay. Okay, and then let's see. So let's try different one. Let's try X. Okay, let's do paper searching on the JSON metric. Okay, and then see the graphs. Okay. So we'll do depth first searching a JSON matrix. Okay. So this one actually first you need to build a graph, and is using this kind of the matrix. Okay. After you get that, you will do depth first searching. Okay. Kicking on your starting node. So you build the number of the graph as vertex of y. Okay, age, you create 4 age. So you add the 4 age related information. It's 0 to 1, 0 to 2, 0 to 3, 0 to 4. So actually it's a node called 0. And then it actually connecting to 1, 0, 1, 2, 3, 4. Okay. So that's the graph like this. Okay. And then after that, actually, there's a depth first searching, and you need to keep track of a vector of pool. So this is the same as we use the VDT metric. Okay, and then you get started from the starting node. You see and set the VDT to be true. Okay, and then you go through every node. Okay, and then if VDT if it is not VDT, then you will go and VDT. So that is depth first searching. Okay. Okay, so this one pretty easy. Okay. This one pretty easy. Let's just copy it. So this one is called graph matrix. Okay, depth first searching. Okay. So this one, you actually have 5 vertex, 4 edge, and you add a different edge to it. Okay. And then you actually create a metric. This one, actually, the metric is not two-dimensional array. It actually is a vector of vector. Okay, using the vector of vectors. So here, remember, you need to have extra space right there. Okay, otherwise it won't work. Okay, but vector of vectors, it can also be considered as a two-dimensional array. Okay. And then you created a VDT vector and put in the force in there. Okay. And you get started from node 0 with the empty VDT to VDT them. Okay. And at age, okay, depth first search start with VDT. You print the node and then you set it to be VDT. And then you go for the neighbors that are not VDT recursively. That's it. This is pretty simple. Okay. So we did 0, 1, 2, 3, 4. Okay, this one pretty easy. Let's try another one. Okay, next one, let's try breadth first searching using a JSON metric. Okay, so here is another example called breadth first searching using a JSON matrix. Okay, the graph is like that. Okay, let's actually copy it as well. Okay. Okay, this one is breadth first searching. Okay, so here you have 5 vertices. Again, you create a JSON metric or two-dimensional, okay? And then your 0 connected to 1, your 0 connected to 2, and 1 connected to 3. This is the graph that you have. and then you get started to for your traversal from your starting node 0. Okay, so when you do breadth-first searching, okay, you started from node 0, and then you put the neighbors into a queue, and then you get the first node out, and you put the neighbors to the queue. And then you actually visit the first node and you put the neighbors into it. Okay, so you actually go visit every node. You put the queue. Okay, if the queue is empty, you get out. Okay, otherwise you get the first element in the queue. And then you do erase it. Okay, erase it means you already visited. Okay, and then otherwise you go visit every node that you have. Okay. You go visit every node that you have. So you need to set, when you visit every node, you set it to be visited. And then you go visit every node recursively. Okay, and that's it. This one also very simple. Okay, so you visit every node. So today we actually finish this one, the adjacent. We actually finish the adjacent list, and then word later problem, and then adjacent matrix. So these are different traversal way. Okay, so we go up to here. Okay, now this portion is the building of the graph. Okay, building of the graph. Depth first searching, breadth first searching. Next one, we are going to go into the problems. Okay, go into the different problems. It will become the problem solving using graph. Okay, we'll go into the problem solving using graph. And the most important one would be topological sorting, shortest path problem, minimum cut problem, minimum spread tree problem. Okay, these are typical important graph algorithms. Okay, and we will be doing that the next week. Okay. Hi, Shirley, are you okay so far? Okay. Hi, Shirley, are you okay so far? So because today, both Helen and Cheryl are not here, so we are going to stop right here, okay? Because we don't rush too fast. Next one, we are going to go to the ninth keyword problem. We are going to solve problem by problem using the graph, okay? And then the implementation today, we actually do have a adjacent list using node, and the adjacent list using vectors, and then this one adjacent matrix. These are the typical simple graph building techniques. Okay, and we will be using it when we start to solve the problem using graph. Okay, and then if no question, that's it for today. Okay, see you next time. Bye bye.